Let us take two more questions from the chapter Conservation of Momentum based upon spring mass systems. So this question here says two blocks of masses m1 and m2 are connected by a spring of spring constant k as shown in the figure. Now each of the blocks is pulled by a constant force F acting in opposite directions. Find the maximum elongation that the spring will suffer and the distances moved by the two blocks in the process. Good question in terms of understanding how the law of conservation of momentum work here and how it helps us find out the answers. Do we understand that if we consider the two blocks and the spring as a single system, then there is no net external force on the system? This F and this F both are equal and opposite. So no net force. F net is 0. If F net is 0, we understand that the acceleration of center of mass of the system will also be 0. The center of mass is not going to accelerate. And what is the initial state of the center of mass of the system here? Can we say the center of mass is here somewhere? Initially the center of mass was at rest. Before the forces came into picture, it was at rest. So if it is at rest, it will continue to remain at rest because the velocity of center of mass does not change then if the acceleration is 0. Velocity of center of mass is constant, which in this case is 0 because initially the system was at rest. So the center of mass of this system is not going to go anywhere as the blocks move under the effect of the external forces. So do we understand that if we look for the case where the spring comes in its maximum elongation state, that will be the state when the center of mass being here itself, the blocks have moved certain distances over here and over here, right? M1 reaches somewhere here, M2 reaches somewhere here, such that the displacement of M1 is, let's say, x1 and the displacement of M2 is, let's say, x2. If we have to ensure that the center of mass does not shift in this process of the movement of the blocks, can we say M1 x1 should always remain equal to M2 x2? This is the condition for the center of mass to remain at its own place, right? Now the next thing, how do we find out the values of x1 and x2 individually? So do you understand that for that we have to get another equation which we can get here from by using the work energy principle, the work energy theorem. How do we use the work energy theorem here? Do we see that as the two blocks move under the effect of the forces F each on both the blocks, these forces will do some work on the blocks? So can we say by work energy theorem, which says that the work done by all forces should be equal to the change in the kinetic energy of the system, right? So can we say what all forces do work here is work done by the external force F, which in this case will be, if we assume that the mass m1 moves a distance x1 to the left, the work done by the force that acts on m1 will be F into x1 plus the work done by the force F which is acting on m2 will be F into x2 if we assume that the block m2 moves a distance x2. This is the work done by the external forces plus what will be the work done by the internal spring force. Remember that in work energy theorem we consider the work done by all forces, whether they are external or internal. In this case, do you understand that the spring does work because the spring undergoes a change in its state? What will be the work done by spring? By definition, the work done by spring is the negative of the change in its potential energy. So it will be minus half k into, do we see that if the block moves, two blocks move x1 and x2 towards left and towards right, the total extension that the spring will suffer will be x1 plus x2. So can we say the change in the potential energy of the spring will be this? Initially the potential energy was 0, finally the potential energy is half kx squared. So x here is x1 plus x2, right? Can we say this is the work done by the spring? And this should be equal to the change in the kinetic energy of the system of the two blocks. Initially these blocks were at rest, so no kinetic energy initially. Finally, when they reach the maximum extension state of the spring, do you understand if they have reached a maximum extension state of the spring, that means they are once again at rest. because if they would continue to move, then the spring will further stretch, right? So can we say that if the two blocks have reached the maximum extension of the spring state, that means that they are at rest once again. So the final kinetic energy of the system will also be 0 then. That means the right hand side of this equation is 0. So we get an equation, one more equation in x1 and x2, right? So we can use this equation now into the second equation over here and get the value of both x1 and x2 and also the value of the extension in the spring. Understand that the extension in the spring x will be nothing but x1 plus x2, right? So let us solve for this now. How do we solve it? The first thing is, if we solve this particular equation slightly, we can take f common here, write this as x1 plus x2 and take this term on the other side of the equality sign so that it becomes half k x1 plus x2 whole squared. One term in x1 and plus x2 will cancel out on both the sides, and from here we can easily get the value of x1 plus x2, which will come out to be 2f by k. Understand that x1 plus x2 is nothing but x, the extension in the spring. So this is what we have got, and now we can use this equation along with the first equation here, m1 x1 is equal to m2 x2, to get the values of x1 and x2 both, right? So can we do this? Can we take the value of from the equation m1 x1 is equal to m2 x2, can we write, let's say, x2 is equal to m1 x1 by m2, and then substitute this value of x2 over here to get the value of x1. So we get x1 from this equation plus m1 x1 by m2 is equal to twice of f by k. Solve this for the value of x1. So when we solve this, taking x1 common, 1 plus m1 by m2, we can take an LCM to get m2 plus m1 by m2 is equal to 2f by k, and from here now we can get the value of x1 as 2f by k times m2 by m1 plus m2. And now by symmetry, we can say that the corresponding value of x2 should be 2f by k into m1 by m1 plus m2. You can verify this by substituting this value of x1 into this equation and getting the value of x2. Okay. So all the three values we have got. This is the elongation of the spring, and these are the two displacements of the blocks. Now we have another similar question over here, but slightly different. Let's see what it is. It says, consider the situation of the previous problem. So we still have the two blocks connected with a spring. Suppose the block of mass m1 now is pulled by a constant force f1 and the other block is pulled by a constant force f2. Find the maximum elongation that the spring will suffer now. So this is slightly different, this question, because now if we see, since f1 and f2 are not equal forces in magnitude, the net external force on the system is no more 0. In fact, it will be, if we just assume that one of the forces is bigger, we can say that the net force will be, let's say f1 is bigger, so f1 minus f2 now will be the net force acting on the system, and it is not 0. Which means that the center of mass will have an acceleration this time, right? So the whole system, the blocks along with their spring, they will accelerate, continue to accelerate with a certain acceleration, which we can actually find out. Acceleration of center of mass, we can say, will be the net force divided by the total mass of the system, f1 minus f2 divided by m1 plus m2. This is the acceleration of the center of mass, right? Now, how do we simplify this situation? Because otherwise, if we work from the ground frame, this question will become quite complex, because we don't know what condition to put for finding out the maximum elongation of the spring. At what situation will the spring have maximum elongation? Because we know that the system will continue to accelerate. The center of mass of the system is accelerating all the time. But we can simplify this equation by working in the frame of the center of mass. When we say we try to work in the frame of the center of mass, understand that that would mean that the center of mass remains at rest. In its own frame, the center of mass will remain at rest, isn't it so? And if the center of mass comes at rest, then we can once again use the same condition that we have used in the previous question, that at the maximum elongation of the spring, the two blocks will be at momentary rest, right? So can we say, in the frame of center of mass Cm, if we have to work in the frame of center of mass, we can use the condition for maximum elongation of the spring, right. Now, in order to work in the frame of center of mass, because center of mass is accelerating, we need to take the help of pseudo force if we want to work in an accelerating frame, right. So, we know in the frame of center of mass, which is an accelerating frame now or a non-inertial frame, this is an accelerating frame. So, we have to use a pseudo force to be used, right. What will be the pseudo force acting on the particles? We know that the pseudo force that acts on any body of mass m which is being studied from a frame which is accelerating with an acceleration a is m into a, and the direction is opposite to the direction of acceleration of the frame. This is the expression, right. So, can we say if we want to work in the frame of center of mass now, we will consider this mass m1 attached through a spring with the mass m2, and now if we look at the forces that are acting on them, F1 and F2 are the original forces, F1 here and F2 here on M2. Apart from these two, there will be pseudo forces acting on the two blocks corresponding to the acceleration of the frame being the acceleration of center of mass, which is now F1 minus F2 by M1 plus M2. This is the acceleration of the frame in which we are now studying the system. So, can we say, and what is the direction of this acceleration? Understand that we have taken F1 to be a greater force. That means we are assuming that the net force on this system of two blocks is towards left, towards the direction of F1. That means the acceleration of center of mass is also towards left. And if the acceleration of center of mass is towards left, we have to take the pseudo force on both the blocks towards right. So, here the pseudo force acting on M1 will be the mass M1 times the acceleration of center of mass towards right, whereas on M2 also the pseudo force will be M2 into the acceleration of the center of mass. So, in the center of mass frame where the center of mass is at rest, not moving at all, these are the forces acting on the two blocks. And now we can use the same work energy theorem to get our answer for the maximum extension in the spring. If we assume that, let us say, the block M1 moves a distance x1 towards left and the block M2 moves a distance x2 towards right under the effect of these external forces F1 and F2, and now there are other forces also, we can say that by the work energy theorem, which is the net work done is equal to the change in the kinetic energy, work done by F1. So, what is the work done on the first block now? The work done on the first block will be the net force on M1, which is F1 minus M1 into ACM times the displacement x1. This is the work done by the net force on M1, plus what is the work done on M2 by the net force acting on M2. See that the net force on M2 is F2 plus M2 into ACM, because both the forces are acting in the same direction, times x2. And what is the work done by the spring then? Plus work done by the spring will be negative of the change in potential energy of the spring. So, minus half K into the extension in the spring will be x1 plus x2, as we have discussed in the last question also, the previous question. So, this is the change in the potential energy of the spring, and this should be equal to the change in the kinetic energy of the system, which will be 0, because initially the two blocks were at rest, and finally when the spring reaches in its maximum extended state, the two blocks will once again come at momentary rest. So, this is our equation now, and this is the one that we have to solve. Physics over, now we have to deal with the mathematics. So, substitute the values. In this equation, we will have F1 minus M1 into, what is ACM? ACM is F1 minus F2 over M1 plus M2. This into x1 plus F2 plus M2 into F1 minus F2 over M1 plus M2 times x2, and now we take this term on the right hand side of the equality sign. So, we get half k into x1 plus x2 whole squared. Let us simplify this further. Let us open this bracket up by taking an LCM. When we take the LCM, we shall see that a few terms will cancel out. See that when we take an LCM m1 plus m2, we will have f1 into m1 plus m2 minus m1 into f1 minus f2 divided by m1 plus m2, isn't it? This times x1. In this term, see that the term this is m1 f1 and this is m2 f1, the first two terms, and here we have minus m1 f1. So, see that minus m1 f1 will cancel out with plus m1 f1 here, right, and we will be left with f1 m2 plus f2 m1, right, divided by m1 plus m2 times x1. This is what we are getting in the first term. Similarly, now when we solve the second term, on taking LCM, we will have f2 into m1 plus m2 plus m2 times f1 minus f2 whole divided by m1 plus m2, and this whole thing times x2. So, see that in this case you have a term of minus m2 f2 and a term of plus m2 f2. So, this term and this term will cancel out and we will be left with f2 m1 plus m2 f1 divided by m1 plus m2, and this whole thing multiplied by x2. This is equal to half k x1 plus x2 whole squared. Now, if you look carefully, these two terms are actually the same, identical terms these are. So, we can take them common and we can write m1 f2 plus m2 f1 taken common, inside we will be left with x1 plus x2 whole divided by m1 plus m2, right, and this is equal to half k x1 plus x2 whole squared, and one term in x1 plus x2 will cancel out throughout. What we are looking for here is the extension of the spring, which is nothing but x1 plus x2, right. So, we keep this x1 plus x2 on the right side and take all the other things on the left hand side, so that we get 2 by k times m1 f2 plus m2 f1 by m1 plus m2. This then becomes our final answer for the extension, maximum possible extension in the spring in the given case.